Hi folks, and welcome back to my basement. I am here today to re-record the first part of example 7b, which I did cover in class yesterday, but I neglected to check that the audio input from my microphone was programmed correctly into the recording software. So, amateur move, for which I get the pleasure of redoing this lecture. So, what we had discussed at the beginning of class prior to actually jumping into the example was terminology and significance testing and effect size with respect to time invariant predictors. So that's the magical word here. Time invariant predictors in a setting of longitudinal data analysis can also be referred to as person characteristics, time constant predictors, level 2 predictors, between person predictors. The idea is that these are variables that have only been measured once, so we don't know if they changed or not. Presumably they've been measured once because people expect them not to have changed, but the idea is that they are measured once per person, and so they are treated as person characteristics. They represent between person differences in phenomena thought to relate to whatever outcome we're modeling. Because level 2 predictors can only have fixed slopes in two-level models, we don't have to worry about testing random slopes. And because we are using residual maximum likelihood estimation in this example, we cannot use likelihood ratio tests to talk about the effects of these predictors contributing to the model. When REML estimation is used, models that differ in their fixed effects are not comparable with -2 log likelihood AIC or BIC. Consequently, we will rely on Wald tests to judge the significance of any new level 2 predictor slopes, where each individual slope can be tested with the usual univariate Wald test of estimate divided by standard error is treated as a t, with denominator degrees of freedom estimated as part of the model. Satterthwaite method is being used here as usual. And if we want to test multiple slopes of a time invariant predictor at the same time, such as the overall contribution of the predictor to predicting intercept and slope, then we can lump slopes together to do a multivariate Wald test, which is a custom F test for the contribution of that set of slopes. So it will be directly analogous to the idea of testing change in R-square in single level models. We can do so using the same type of custom F test for the new slopes that would contribute to the model R-square in these models as well. In terms of effect size, we can differentiate two distinct and complementary ways of indicating effect size. One is pseudo R-square, which is a per pile measure, and as discussed, if you'd like to sound more formal in your writing, rather than talking about them as piles of variance, you would talk about them as variance components or sources of variance. Pseudo R-square is used to indicate the proportion reduction in each pile due to a corresponding new fixed slope. So we would compute pseudo R-square for the random intercept variance as a function of any main effect slopes of a level 2 predictor. We would compute pseudo R-square for slope variance when that level 2 predictor is entered as an interaction with that corresponding level 1 predictor. So for instance, time as a level 1 predictor as part of a cross-level interaction would predict the cross-level interaction would predict that random time slope variance. So those are specific measures of effect size that describe how well each distinct type of variability was predicted by the model. And as an alternative, we can also talk about total R-square, which is directly analogous to R-square in single-level regression models. What we will do is compute the predicted outcome from the model fixed effects, correlate that predicted outcome with the real outcome, square that correlation, and that becomes total R-square. So it's the total amount of variability that has been explained or accounted for by the model fixed effects. There was a question about why don't we include the random effects in generating the predicted outcomes? And my response was that that would be cheating. Here's my logic. Random effects represent unknown sources of individual differences. So in estimating a random intercept variance or a random time slope variance, we know that people need their own intercepts, and we know that people need their own time slopes. What we don't know is why. So because we don't know why, random effects conceptually are still error variances. So adding in a random effect into a predicted outcome is adding in unexplained variability essentially back into the prediction, which is not cool. So in these examples, I am generating predicted outcomes using only the fixed effects so that I can think about explained variance in the traditional way. All right, I think that's everything that we talked about to start off with this example. These data are the same data featured in example 6. So we have 6 sessions of practice in a task where response time is the outcome. These 6 sessions happened over a 2-week period. So even though these are older adults as the subjects in this example, they are not aging per se over a 2-week period. So age is going to be one of our time invariant predictors, and the other is going to be abstract reasoning, which is an indicator of fluid intelligence. This example is going to only have R matrices with a diagonal structure where the variance on the diagonal is held equal across occasions and there's no residual covariance. Consequently, we don't need to refer to the SAS repeated statement, the stated residual statement, and we can do all of the models using Elmer in R rather than switching to the LME or GLS functions within the NLME package instead. So I had went over the data import and variable manipulation. As is my convention in doing my own analyses, I put together all variable and data transformations in one section of my code. That way, when I return to my file, I can just run that section and get back to where I was rather than having new variable definitions scattered throughout the package or the program. So within the SAS code, of course, to start with, I am importing a SAS data set into the work library. So I'm basically saving it as a copy of itself so that I can work with it without damaging the original. I'm creating time variables, so time with 1 as a suffix. That was meant to have consistency with my naming convention of new variables where the centering constant is stuck on the end. It's sometimes time in my examples, it's sometimes time 1. I go back and forth as to which one I like better. Today it's time 1. So this is going to be used in fitting models of linear and quadratic change in the second half of this example. The first half of this example is going to use the same 2 piecewise slopes that were found to fit relatively best and not worse than the saturated means unstructured model in example 6. So that would have been example 6b, in which these slopes were initially introduced. So if session is equal to 1, that's what that means, we initialize both of our slopes to 0. That means that session 1 is going to be my model intercept, where time equals 0 for both of my slopes. Otherwise, if session is greater than or equal to 2, the first slope switches to 1, the second slope switches to session minus 2. So that creates the pattern of 0, 1, 1, 1, 1, and then 0, 0, 1, 2, 3, 4 that we would see for the second slope. So we would call slope 1, 2 the idea of initial practice or early practice. Slope 2, 6 then maps onto the idea of subsequent practice in which response time does not improve as quickly as it did initially. Our level 2 between person time invariant predictors are created here. So based on their descriptive statistics, I picked 80 as my centering point for age, which was near the mean, and I picked 22, which I believe is a number correct out of 30, which was near the mean for this variable of abstract reasoning. So my reference person in these analyses is going to be an 80-year-old who has average level of fluid intelligence. And then last but not least, I wanted to show an example of what it would look like in the code if you had a categorical or grouping variable instead. Not having one as part of this data set, I made one. So only for demonstration purposes only, I cut up education into 3 categories, where less than or equal to 12 years is a high school degree, greater than 12 years or less than or equal to 16 years was a college degree, and then greater than 16 years of education was a graduate degree. Then finally, because it would happen anyway, because rows that do not contain all of the variables in the model will get deleted anyway, I have removed cases that are missing on any of the variables eventually to be included. If you have a lot of missing data, this is not a good idea. If you have just a little bit, what this does is enable your sample to remain constant across models, regardless of whether you have a particular variable in that model at that time or not. So the SAS function I'm using is nmiss, which computes the number missing across these columns. I'm saying if the number missing is greater than 0, then delete those rows. So any rows that are incomplete with respect to these 5 variables will be removed. And then here's the code to generate descriptive statistics that I use to decide on the centering values for age and reasoning. In the stata code, all of this looks familiar to what we had done before in the example 6 models. We have time 1 as my linear effective time. I had to generate time squared explicitly as a variable in stata to be included as a random slope. I also have my piecewise slopes. And because I don't know how to do this more efficiently than this in stata, it takes more code. If anyone out there can help me by allowing multiple things to happen after one conditional if, let me know. I would appreciate that. Here are the 2 new predictor variables for level 2 between person differences being created and centered here. And then here is education being chopped up into groups. Last but not least, I'm using an egen, which is a fancy way of generating a new variable using functions, to make a new column called nmiss that is equal to the number missing for that row across these 5 variables, and then I'm dropping cases where any missing values are there. So same as in SAS using the nmiss function, and getting descriptive statistics. In R, then, I am importing the SAS version of the data set. I'm converting it to a data frame. This is sometimes necessary and sometimes not, and I've given up trying to figure out when, so I just include this code, so it might be redundant, but it doesn't hurt anything if so. I am then creating my linear time variable, which will be squared for the polynomial models, as well as my piecewise slopes coding. So here's the coding scheme that I described earlier. Here are the new level 2 between person predictors being centered at age 80 and reasoning 22. I found a function called cut. I'm not sure where I got it from, but it will be inside the online files if I required any additional packages. And that cut up education into the 3 groups that I wanted for demonstration purposes only. To make the output for education match that of the other programs in which the last category is the reference, I used relevel to change it into a new variable where the reference is the last category. And then I did a complete cases function referring to the numbers of the columns as to what I want complete cases across, and dropped cases that are missing anything in those columns. And then finally descriptive statistics. Okay, so first set of models in this example is going to be piecewise models for 2 reasons. Number 1 is they're easier conceptually to work through the addition of time invariant predictors. And number 2, because we found earlier that this model fit relatively best. Even though it's atheoretical, it did the best job of approximating the saturated means and all of the unstructured variances and covariances across my 6 occasions. So in this multi-level model equation, I have taken the extra step of labeling what each of these betas is conceptually to help us figure out what the level 2 equations are predicting. I tend to do this because it makes my working memory load reduced. I do this in papers, I did this in the book, and I would encourage you to do this too to help out your readers understand what you're referring to. So beta 0 is how each person gets their own intercept, beta 1 is how each person gets their own early practice slope, and beta 2 is how each person gets their own later practice slope from sessions 2 to 6. And the gammas here, the y-looking things that start each of these level 2 equations, those are the fixed effects. So fixed intercept, fixed slopes. The u's are the random effects, so they are there to represent the idea of individual differences. Rather than estimating a u per person, we instead estimate the variance of the u's across people as the model parameter. So we have a random intercept variance and 2 different random slope variances. That means that people differ from each other in 3 distinct ways according to this model. And that means that any level 2 predictor has 3 distinct roles that it can play in predicting each of these sources of individual differences. To help us reconfigure the model fixed effects into simple slopes once we include interaction terms, I've also replaced the beta placeholders here, filled them in directly with their fixed effects, and eliminated all of the parameters that refer to the model for the variance so that I can create an equation for y hat. So the predicted y from the model fixed effects. At this point, all we have is a fixed intercept and two fixed slopes. This y hat column is going to be saved to the data set in the code below so that I can correlate that y hat predicted outcome with the real one and square that correlation to generate a total R square. And one more note with respect to terminology. In the models that we've seen in this class, there's 3 different words that I use to describe what they contain. 1 is empty, 2 is unconditional, and 3 is conditional. Empty means absolutely nothing in the model with respect to predictors, only a fixed intercept if it's an empty single level model. If it's an empty multi-level model, it would have a fixed intercept and a random intercept, but no predictors of any kind. Unconditional, which is the word that I've used here, refers to the idea of unconditional model for change, meaning only effects related to time are in the model. So any fixed slopes to describe average change over time, any random intercepts and slopes to describe individual differences in intercept and change over time, and any alternative covariance structures among the level 1 residuals that are needed to describe residual correlation over time. So the unconditional model then is our new baseline because it contains as much variability in the random intercepts and slopes as there is in the data. Now our job is to see by how much we can reduce each of these U variances by adding level 2 between person, time, and variant predictors. So this is estimated to become a baseline so that we can see how much variance there is to be predicted at level 2. So slope 1, 2, and 2, 6 go in the model as fixed effects here on the model line in SAS. They go into the random statement to become random effects as well as the intercept, of course, that we have to start with. This piece of code right here, out PM, what that does is create a copy of the analysis data set whose name is given after the equal sign. So pred p unc in my notation means this is the data set that's going to have predicted values from the piecewise unconditional model. It's going to have a bunch of columns appended to the end of the data set that have the prediction and the standard error. So the column that contains the prediction is going to be called pred. Down here in the proc core, I then go into that data set. I ask it to compute the correlation between the pred predicted outcome column with the real outcome, and that's going to become my total R. I will then need to square it to become total R square. I also had saved that to a data set to do something separate with it. Likewise, these ODS output commands save the covariance parameter estimates, so all of the parameters in the model for the variance, so that I can use them later to do pseudo R-square calculations against a model with predictors. In Stata, we have the fixed slopes entered here after the outcome in the mixed line. The random slopes are here after the bar. What's not written but implied is the random intercept, which was basically that space right here. I also have a new line here, the predict function. So what this is going to do is create a new column in my data set that is named pred p unc. And so each column must be named separately. You can't have the same column names in Stata. Last but not least, another piece of new code is right here. I am asking for the correlation between that predicted value column and the real outcome, and then I am asking for that correlation that is saved internally to be squared and displayed. So this part is basically a calculator that's going to show what the total R square is from squaring that correlation. In R, we have the fixed intercept and fixed slopes right here, the random intercept and random slopes right here. The new piece of code to generate predicted outcomes is right here. I'm using the predict function. I want to use the results of the p unc saved model here, again, piecewise unconditional, The option re.form equals NA means do not use the random effects in creating the prediction. So the predicted column is going to be based on the fixed effects only. That column is called pred p unc. So then I'm using core test to correlate that column with the real outcome, Pearson correlation, then displaying that R, and then asking for the squared version of that R to be squared, which will be the total R squared. So in terms of SAS output then, I've asked for the G correlation matrix, which is the correlation among the random effects, to keep an eye on it. In these models, as the random effect variances become smaller and smaller, it may be possible that some of them essentially become identical, so perfectly correlated, which means that your model may need to be simplified. So keeping an eye on the correlations sort of collapsing in, the terms collapsing into each other can be helpful. I have labeled all of the model for the variance terms here. You're welcome. So yes, these words at the end here, if you're looking on your SAS output for the explanations, you will not find them. This is just me being nice. So we have UN11 is my intercept variance, UN22 is my random slope 1,2 variance, and UN33 is my random slope 2,6 variance, as well as my level 1 residual as the fourth variance component. Any of these terms that have different numbers in the parentheses then refer to row-column covariances. Likewise, fixed effects, I have them labeled here as to which fixed effect that line of output is referring to. So the intercept then is the predicted outcome when time equals 0. Given my piecewise coding scheme, the predicted outcome at time 0 is at session 1. So at the first occasion, response time to this task is about 1962 milliseconds. From there is a change of minus 163 milliseconds on average to go from session 1 to session 2. So response time is improving on average. And then after session 2, there is a more shallow rate of change of 33 milliseconds per session, indicating that the effective practice is less after session 2 than it is initially. In terms of the effect size for this model, those two slopes have created a predicted outcome, pred here, that is correlated 0.19 with the real one. If I take that 0.19 and square it, I end up with a total R square of about 0.04. So 4% of the total variation in response time is because of change on average. Now we can see by how much that will increase as we add slopes for our time invariant predictors. Starting with age. So in the context of cognitive aging research in which these data were collected, age is a covariate that has to go into your model regardless. So chronological age has to be controlled for before you can talk about anything else. Turns out chronological age is not really that interesting of a variable because people have quite a lot of variety in the effects of age, as well as in the extent to which there's cohort differences of people of different ages. So age goes in so that we can talk about the effects of everything else after controlling for age. To help your reader understand what your model means, it's helpful to show the centering as part of the model equation. So whenever you write equations in a paper, you do need to write words explaining them, but for those people who don't want to read the words, having the equation be as transparent as possible is helpful. So I've explicitly shown the centering of age minus 80 here. Note that age gets an I subscript only because it is a person characteristic at level 2. It does not vary over time, unlike the predictors that go into the level 1 equation, which do vary over time. So because we have 3 distinct kinds of individual differences, we have 3 distinct slopes of age that can be used to predict them. So gamma O1 is going to become the main effect of age, and that is shown a little more readily if you look at the fixed effect predicted outcome here, in which I have swapped out the beta placeholders and removed all of the terms from the model for the variance. So gamma O1 is the multiplier for age as a variable by itself. Likewise, gamma 1,1 and gamma 2,1 are the effects of age on each of the slopes. Those are known as cross-level interactions because age is a purely level 2 variable, whereas slope 1, 2 and slope 2, 6 are purely level 1 variables. And again, the combined equation here, after substituting the beta placeholders, shows the fact that these are interaction terms more directly. So I've also shown over here in this box, to help you with homework and the rest of your life, examples of how one would generate model predicted conditional slopes at any values of the moderating predictors. So in particular, these two interactions can each be interpreted two distinct ways. The more obvious choice in this context is to think about how age moderates the rate of change due to practice. So the formula for computing simple slopes is to go into the model equation, find all of the terms that have the slope of interest in them. So if I'm building a simple slope for slope 1, 2, I need to grab gamma 1, 0. Don't need this, don't need this, do need this one, don't need that one. Then I factor out slope 1, 2, and what's left is the basis of the estimate statements in SAS, Lincom statements or margins in Stata, and contest 1D when we're using Elmer and R. So this shows then that the fixed slope is specific to somebody who is 80, because that's the only situation in which this part would drop out. Likewise for this one. And otherwise, what would go as the multiplier for the cross-level interaction is the age for which you want slope 1, 2 and slope 2, 6. The other way to think about these two-way interactions, rather than talking about how age moderates change, it would be how the effect of age differs over time. So the only point in which these terms drop out is if they're 0, which would be at session 1, in which case the slope for age would only be the main effect. Otherwise, we would fill in multipliers that correspond to the coded values of slope 1, 2 and slope 2, 6 when they were initially created. So what are the values for that occasion for these two variables? That's what goes in here. In terms of adding our three new slopes, they get added to the fixed effect portion of the model. So here it is in SAS, for instance. Also in SAS, I have asked for a custom f-test using contrast. What this statement does is lump together the main effective age and the two age interactions. It understands that I want a joint hypothesis test of three separate slopes because I have divided them with these commas. Yeah, that. Otherwise, it would try to add them together if I didn't have the commas. So this is answering the question, does age contribute to the model? Another way of thinking of it is, I'm going to end up with an increase in the total R-square after adding age. Is that increase in the total R-square significant? The answer is given by this hypothesis test of those three slopes. I also have examples of how to request simple slopes. So slope 1, 2, for instance, I am requesting it for prototypical values of age. Typically, people choose -1 standard deviation, the mean, and +1 standard deviation. So in these data, that's around 6. So I've requested slope 1, 2 for a 74-year-old, 80-year-old, and 86-year-old. So that statement that's highlighted here is the same. If I can highlight both, not quite. The ingredients for it are given right up here. So I need one of the fixed slope 1, 2, and then I need as many interaction terms as for the age for which I want slope 1, 2. So this is for a 74-year-old, given that 80 is the centering point. I do the same thing in requesting prototypical slope 2, 6s at different ages as well. Then to spin the interaction from the other direction, we can talk about how the effect of age changes during the study. And then the multipliers given to the interaction terms are not the age that I want them for, it's the occasion that I want them for. So the 0, 1, 1, 1 matches the coding of time when we're creating the initial slope 1, 2, and 0, 0, 1, 2, 3, 4 is how slope 2, 6 was coded across the 6 occasions to capture the change from 2 to 6. Last but not least in the SAS code, I wrote a macro that does total R square. The input to the macro is it wants to know what the outcome variable is, it wants to know what the data set is that contains the nested model, and it wants to know the data set of the augmented model. So I'm asking for a total R square relative to the unconditional model for the effects of adding age. Pseudo R square is another macro that I wrote. It wants to know the total number of parameters in the model for the variance. So that's the number of rows in the covariance parameters table output. It wants to know what that output is called when it was from the nested model, so the model with fewer parameters, and then from the augmented model, the model with more parameters. So this is 2 additional pieces of output that we'll get from this run. In Stata, the new effects of age are entered as fixed effects right here, where again the hashtag or # is used to indicate interaction terms on the fly. The test statement here is used to lump those 3 slopes of age together for a joint hypothesis test, where the small option then is asking it to use the same degrees of freedom method as for the model estimation. I have lincom statements here for demonstration purposes of how one would ask for simple slope 1, 2s for any age, but those 3 lines can be done more efficiently with this single call to margins and the dydx command. So it's asking for the derivative of the function with respect to slope 1, 2, so you can get the different ages at which you want that slope. And it does require you to input something for denominator degrees of freedom because it doesn't have a small option. So I picked what it ended up being in the model output from SAS. Same thing here for the slope 2, 6, reminding myself that I still need to make these things green. In case you're wondering how I do this, let me do this in front of you so you can appreciate how tedious this process can be. I find the right color green, and then I go through and manually apply it to anything that is not in the right color. I figured out how to automate some of this, but not enough of it. There. That's better. These latter commands then are asking for the simple age slope at each session, and that requires 2 different calls to dydx to do that more simply here. I'm asking for predicted outcomes and making a plot of them, as well as then correlating the predicted response time with the real one, and then displaying the square of that correlation as total R square. Which means, yes, I skipped over this line. This is where the y hat column is being generated from this model. In R, then, we have the new effects of age right here, where a colon is used to generate interaction terms on the fly. I have seen R yell at you if you label them one way up here and then refer to them differently within subsequent hypothesis tests. My convention is to list the variable that was included first as the first part of the interaction term. We have a contest MD statement right here that is going to generate the custom F test for the contribution of the 3 age slopes jointly. The way that you make these statements is to start by providing as many values as you have fixed effects in the order in which the fixed effects are shown in your output. Not necessarily the order in which you wrote them, but the order in which they appear in your output. So the order in which they're in the output is consistent with how they're written here. So I usually start by writing, as many zeros as I have terms to be filled in. So placing a 1 in the 4th column means, hey, I'd like this one. Placing a 1 in the 5th column means, hey, I'd like this one. And then the last column refers to this one. The commas in between then help indicate that this is a joint test of 3 slopes, not that I want the slopes added together or something like that. Then I can use contest 1D, so 1 dimension versus multiple dimensions, to create the predicted simple slopes at different ages. So here I have a 1 in the 2nd column because I need 1 of slope 1, 2, and then I have values in the second to last column as the age for which I want slope 1, 2. The last three statements, then the 1 switches to the third column because it's slope 2, 6. Likewise, the age values go in the last column for the interaction of age by slope 2, 6. And these are the age values for which I want slope 2, 6. Then the age slopes, same idea, but from the opposite perspective. I have a 1 in the fourth column all the way down because each age slope starts with what the main effect of age is. And then the multipliers of the interaction term give the coded value for that occasion when computing the slope. So 1, 2 is coded 0, 1, 1, 1. Slope 2, 6 is coded 0, 0, 1, 2, 3, 4. Again, using the predict function to create a column of predicted values, correlating that column with the actual outcome values, squaring that correlation, and then lastly computing the change in R-square relative to the previous model. So here's my output. So these variance components then should be smaller to the extent that age matters in predicting individual differences in intercept and in each slope. We'll see the exact difference in the variance components in the output just a second. In terms of the solution for fixed effects, we can think of these three terms as working together to describe the reference growth curve, and in this context it's actually a decline curve, not a growth curve. Given the effects of age, the main effect moderates the intercept, the interactions of age moderate each slope, so that means that all three of these terms are conditional on age 80. So an 80-year-old is expected to start out at 1967 milliseconds at the first occasion, to improve by about 165 milliseconds from the first to the second occasion, and to continue improving by about 33 milliseconds a session per session from 2 to 6. Then we went over the interpretation of these terms. Let's see if I can blow this up a little bit. So the slope of age, no mental gymnastics needed for this one. This is just your typical type of slope. For every year older you are when you start the study, response time is higher by about 30 milliseconds. So that's 30 milliseconds per year of age. And that is conditional at time 0, given these interaction terms. So the main effect is always specifically when the interacting predictors are 0. Interacting slope 1, 2 and slope 2, 6 become 0 if we're talking about session 1. So putting that all together, for every year older you are when you start the study, response time at the first occasion is predicted to be higher by about 30 milliseconds. To interpret the two interaction terms, we can talk about how age moderates the slopes to begin with. So if we focus on slope 1, 2 and its moderation by age, I would say that slope 1, 2 is minus 165 for an 80-year-old. It becomes non-significantly more negative per year of age by 7.6 milliseconds. So this pattern of interaction is a more negative. Your choices, just to remind you, are more positive, more negative, or less negative. Every interaction term is one of those four. So this is a more negative, meaning that the effect of the slope is stronger in older people. So older people change more than younger people. Again, not significantly, but I don't care about that. I want you to know what the coefficients mean, regardless of their significance. Likewise, 80-year-olds are predicted to continue improving at a rate of 33 milliseconds a session. That rate of improvement becomes stronger, more negative per year of age by 1.3 milliseconds. So older people put together start out significantly slower, but they change non-significantly more than relatively younger people. All right, so that's all of those. Here are the simple slopes then that illustrate what the interaction terms are doing. So as you can see, the older you are, the stronger your initial slope is. The older you are, the stronger your subsequent slope is. They remain significant at all the points tested here. The effect of age, if we go the other way, let's do that one. So if we start here, this is the age slope at session 1 specifically. It becomes non-significantly less positive by 7 milliseconds at session 2. So it would be 29 minus 7, around 22 milliseconds a session for the age slope at session 2. After session 2, the slope of age becomes less positive by 1.3 milliseconds per session. So we can see the result of those predictions here. So here's the 29 that we started with. Here's the 22 due to the interaction of age by slope 1, 2. And then the subsequent decrease in the size of the slope is guided by these age by slope 2, 6 interaction term. Significant at every point tested. It looks like just eyeballing these that age matters less the more practice people have in the study. In terms of the overall model contribution of age, so there were 3 distinct age slopes added to the model. Here's my custom F-test for their significance. It is significant. That then is the significance test that goes with the change in R-square. So from the unconditional model with just the slope 2, 6 and slope 1, 2 in it, that predicted outcome from those 2 slopes was correlated with the real 1.19 squares, gets us to the R-square of about 0.04. After adding in these 3 age slopes, the outcome that is predicted by the model fixed effects is correlated with the real outcome by 0.33. Squaring that number gives me this number. The difference between my total R-square before versus after is right here. So putting all of that together, 7% of all of the variation in response time across persons and occasions has been explained by these 3 age slopes. That 7% increase in my total R-square is indeed significant as indicated by this F-test. So that's a more general way to talk about the contribution of age. The pseudo R-square values then give us more specific ways to talk about how age is moderating the growth curve. More specifically, UN11, that's my intercept variance. So relative to what it was before, my intercept variance has been reduced by about 10.5%. So 10% of all the reasons why some people were faster initially is because of their age. Likewise, the reduction in the slope 1, 2 variance is about 2%. So this one was not significant. The reduction in the slope 2, 6 variance is less than 1%, also not significant. And there's absolutely no change in the residual variance, which is exactly as it should be, because the main effect of age does this one, the interaction of age with the 2 slopes do these 2, and so consequently there's nothing for age to explain at level 1. Had either of these random slopes not been included, however, then the age interaction with that slope that wasn't random would have explained residual variance instead. So cross-level interactions in which the level 1 predictor is not random, those cross-level interactions explain level 1 residual variance instead. That's why it's important to make sure that all random slopes have been included before testing cross-level interactions. And that, I believe, is where we left off. So we should be caught up to revisit this example and look at the effects of age and reasoning tomorrow. Thanks for being here. See you on the other side.